Start. Start, sir.
Okay. So good afternoon and welcome to this session on the course Heat Transfer. So this is Professor Sunando Dasgupta, and we have two TAs for this course, Miss Manikuntala Mukhopadhyay and Miss Srina Dhara with me, and together three of us. So I guess I was audible to the students who have joined to this meeting, because I cannot see who are there in the meeting. So once again, I welcome you to this session in which we can interact with you and clarify any doubts that you may have about the MOOCs course Heat Transfer.
Sir, the first post in the chat has come, and it's not any question. It's Prithvesh Mandale who is expressing his gratitude for the course as it's beautifully designed, and he says that it has helped him a lot because he's understood the concepts very well, and he said it's because of you he's interested in the subject heat transfer.
Thank you. Thank you. And I hope that your interest in the subject will continue, as well as you will get more interest in other subjects of chemical engineering and be successful. And probably someday we'll meet somewhere, and at least you would be able to recognize me and we can have a discussion. Thank you.
Okay, sir, the second question is Joydeep Paul is asking that can we omit Vx when viscosity is very high?
Can we omit Vx?
Yes, I think he needs to clarify his question.
Joydeep, your question is not very clear to me. What exactly is Vx is not clear. So if you can clarify your doubt, it would be easier for us to answer. So Manikuntala, can they hear what I am saying?
Yes, sir, they can hear what you are
Okay.
saying.
So if the viscosity is high, then obviously the term in the energy equation which contains viscosity cannot be neglected. But in that, if you mean that whether it's viscous dissipation, which has viscosity, and roughly the order is going to be the velocity gradient square. So the viscous dissipation, which is similar to solid friction, is of the order viscosity multiplied by velocity gradient square. So even though the viscosity is high, whether or not viscous dissipation and therefore heat generation is important will most probably be dictated by the velocity gradient. And in the velocity gradient, you have, let's say, Vx, and the direction in which it's changing is y. So it's del Vx del y whole square. So you have a velocity scale and you have a length scale, and square of that is the contributing main deciding factor about viscous dissipation and thereby heat generation. So if that is your question, viscous dissipation will be more dependent not on viscosity but on velocity gradient and the velocity scale and length scale. But Manikuntala, if he has clarified his question, you can relate to me.
No, sir, till now he hasn't replied anything yet.
Okay, so Jaideep, I will wait for clarification from your side if that was the question which you have asked. But in the meantime, I'll keep on answering other students' queries. And whenever your question is complete, I'll come back to it. So if there are any other question, Manikuntala, you can go ahead.
Yes, sir, he has replied. He said ki that is what he was asking for, and he has got his answer.
Okay. All right.
So we have another question where Prithvesh Mandle is asking that sir, can you hear me? Hello?
Yes, I can.
In a non-circular conduit, we use the same correlations for heat transfer. by adjusting the hydraulic diameter. But he's asking that the convective heat transfer, will the convective heat transfer coefficient will get affected because of change in geometry?
There are two different answers to your questions. One is, if you, let's say, instead of a circular one, you have a conduit which is square in cross section. So obviously the corners are going to create locally turbulent conditions even in laminar flow, and therefore the heat transfer coefficient is going to be affected. Now, what is done is, it has been everything is expressed in terms of a hydraulic diameter, which is an approximation. This is not the correct representation of what happens in flow and heat transfer when non-circular geometries are used. So the exact method would be to write the Navier-Stokes equation and energy equation in multiple dimensions, in let's say in x and y directions, solve them simultaneously, use them in the energy equation, and get the heat transfer coefficient. But that is not a practical one when you, as a practicing engineer, will be trying to quickly come up with a number for the heat transfer coefficient. So universally, the use of a hydraulic diameter is accepted as a method for quick calculation with acceptable level of inaccuracy. So that's the answer. It's not exact, but it has acceptable accuracy. First part of your question. If you want exact, you have to numerically solve Navier-Stokes equation and energy equation in order to obtain what exactly is the value of heat transfer coefficient, which at best would be a very cumbersome process and not practicable for quick calculations. Next question.
So,
If he has any follow-up question, I'll definitely try to answer that. If not, I'll move to the next question.
Right now, there are no more questions. If some other question pops up, I'll surely let you know.
Okay.
Okay, sir, we have one more question from Ganesh Sridhar. He first of all thanks you because he is really liking the course. And then he has a doubt regarding lumped capacitance method, where he says that in general lumped capacitance method, it has been described as described in Ingropera. Is it a simplified version from the energy equations?
Okay. First of all, thank you for your comment of appreciation about the course and the teaching. Secondly, if you look at lumped capacitance model, what it does, it's usually temperature is a function of spatial coordinates like x, y, z, and in unsteady conduction problem, it's a function also of time. So t is a function of x, y, z and time, and therefore we get a partial differential equation. We can write the energy equation for this, but we have to keep in mind is that there is no convection, as there is no velocity. It's a conduction process in a solid. So transient conduction in a solid is where we can think of applying lumped capacitance model. So the entire left hand side of the energy equation except the del temperature by del time, except that term would be 0. And then when we come to the right hand side, we have three terms for conduction in the x, y, and z direction. The simplification which we assume in the case of lumped capacitance is that the conduction resistance inside the solid is extremely small as compared to the convection resistance which the solid experiences with at its boundary. So if we go by that, then it converts a PDE to an ODE, where on one hand you have the temperature variation with time, and on the other side you have some parameters present in the system and the temperature. So if you go back to your text, you would see the left hand side contains the time derivative of temperature, and the right hand side contains the temperature as well as a length scale, a heat transfer coefficient, the conductivity, and so on, which when properly expressed would give you Biot number, and the Biot number is just a ratio of conduction resistance and convection resistance, or the other way around, doesn't matter. So what it simply lumped capacitance does is the complicated energy equation is reduced to an ordinary differential equation with the help of isothermal condition in space-wise isothermal condition inside the solid. However, the temperature is allowed to vary with time. So that is the beauty of lumped capacitance. So yes, you can start with the energy equation and still get the lumped capacitance model when you say that T is not a function of X, Y, Z, T is a function only of time. So lumped capacitance, as you have correctly pointed out, can be thought of as a special case of energy equation.
Hello, am I audible?
Yes.
Yes, Akshay Karwade has a question that what is the main difference between Nusselt number and Biot number?
Okay. Manikantan, I would like you to answer this.
Okay, so formally, I think both of them are dimensionless and can be grouped as HL by K. But in the case of Biot number, K is the thermal conductivity of the solid. But in case of the Nusselt number, Ka will be the thermal conductivity of the fluid which is flowing around the body. So I think from a physical point of view, Nusselt number is the general rate of heat which is being transferred between surface and a fluid flow or the surrounding area which is assisting or opposing the directions of the flow. And Biot number, I feel it is a quantity of heat which is transferred to a body of surface via convection, and then it is distributed throughout the body through conduction, or which is subjected to the body capacity so that it can store the thermal energy.
Very good, Manikantan. So I think the answer is clear. The K in Nusselt number refers to the fluid, the thermal conductivity of the fluid, where the K in Biot number refers to thermal conductivity of the solid. So in the case of Biot number, it simply tells us about what's the conductive resistance inside the solid, and the Nusselt number, you obviously know what's the answer. So that's the difference. The fundamental difference is one gives you the conductive resistance inside the solid, the other gives you an idea of the convective resistance at the the fluid side of the interface with the solid. So Manikantra, we can continue, and if anyone of them have if they have any specific follow-up question, please
Yes.
let me know and I'll answer it.
Sir, Joydeep Paul has said that he is understanding the concepts whenever he sees the video, but he is facing difficulties while solving mathematical problems, and he wants your help to understand that how can he get rid of that, or what books should he follow so that he can solve mathematical problems with more ease.
I guess, Jadip, you are referring to numerical problems where the concepts which you are saying that you have understood completely while looking at the video lecture, but you have difficulty in transforming your understanding to the solution of the problem. This is a common problem which happens to many students, so you are not unique. And the only way to get rid of this or to overcome this is to solve more number of problems. The book which I would advise you to follow would be the book on heat transfer by Incropera and DeWitt. If you look at my first lecture, that was a textbook which I have suggested. So it's the book by Incropera and DeWitt, and the title is probably Heat Transfer or Introduction to Heat and Mass Transfer. There you would see a large number of problems have been solved, and even larger number of problems are given in the exercise. So what I would request you to do is you first solve the problems which are already solved in the book itself without looking at them. And then if you get stuck somewhere, then only you look at it. And then once you gain your confidence, you should then try to do similar problems from the exercise, because for each concept you will see 5 or 10 problems provided in Incropera, in the book of Incropera. So to make a long story short, the only way to overcome this is practice and more practice. There are a number of textbooks available. You should just pick a problem which has been solved. Don't look at the solution, solve it yourself and check with the solution provided in any textbook. That I would say is the right way to approach the kind of difficulties that you are facing. Next question, Manikuntal.
Yes, sir. Right now there are no more questions.
Okay.
Ganesh Sridhar, who initially asked about the lumped capacitance method, he's asking that while solving problems for lumped capacitance method, the equation can be directly integrated. Like he's confused whether the equation can be directly integrated or not to get the correct answer.
In most of the cases, lumped capacitance method, if the Biot number is less than 0.1, if you get an ordinary differential equation, yes, you can integrate the equation and integrate the governing differential equation. And with the help of the appropriate boundary conditions, you should get a closed form solution, closed form expression for the temperature, and proceed from there. So yes, it is possible. And for those cases in which Biot number is greater than 0.1, in which case lumped capacitance is not practicable, is not valid, there you have the other alternative approach, which is the Haslard chart that I think I spoke briefly about in the class, in which case with the help of a number of charts for cylindrical, spherical, and planar systems, you would be able to obtain what is the temperature at the center line of the object, how does the temperature, what's the temperature at any given instant at any point inside the solid, and what is the total energy content of the solid, and how does the energy content vary with time, and so on. So for Biot number less than 0.1, when lumped capacitance is valid, you can integrate and obtain an expression. If it is not valid, then the solutions have been provided for simple geometries in graphical form that as a practicing engineer you can use to obtain whatever is required. For example, temperature at a location, the time dependence of temperature, total energy content, and so on.
Sir, Hani Sharma is asking that what book he must follow so that he can perform better at multiple choice questions.
I do not know. I have absolutely no idea. I do not. I cannot honestly answer your question because multiple choice questions generally they depend on what's your understanding. But some people will argue that multiple choice questions can be read, can be memorized, can be answered without going through the fundamentals, without understanding the fundamentals. That is something which I would not discuss in this course. So there are a number of books probably available which would train you for that, but I do not have that answer. But if you have, if you're, what I believe is that if your fundamentals are clear, then the multiple choice questions, you should be able to answer multiple choice questions. But some book which specifically trains you for multiple choice questions and the questions that may come in some definite type of exams, that's beyond this course, and for that you have to do it yourself. Next question.
Sir, we have one more question, but I feel that the framing of the question needs to be a little bit better to
I have
understand.
already answered it.
Yes, sir. Hello. Yes, sir. It's from Prithvesh
Yes.
Mandle, and he's asking that for a particular system, how will you understand that there is no temperature variation in the z direction, or the temperature variation is small, or whether z component of velocity is present or not?
It has to come from the description of the problem and the dimensions involved and the physical properties. So I'll take each one of them separately. The description of the system may tell you that the variation of temperature is unidirectional. That means it varies only with x, that it doesn't vary with y or y or z. So that's a definitive statement which you can use in order to obtain obtain a specific form for the temperature. Second is, if the thermal conductivity is very high and if the dimension in the z direction is small, then it is safe to assume that the variation in the z direction is rather small. So that's a statement which that's something which you can utilize based on your understanding of the system geometry and system parameters. So that's essentially the combination of second and third. Okay, so and if let's say you have a pipe flow in a pipe, and if it's laminar flow, then most likely in order to have a laminar flow in a pipe, you are going to have a flow only in the z direction, not in the r or in the theta direction. So the choice or the use of the term describing the type of flow can give you additional information about the spatial dependence of the temperature in certain cases. That's going to be the third way. And there could be other pointers specified in the problem which should tell you whether or not the temperature is a function of z only, or there is flow only in z direction, and so on.
Sir, he is asking that for a specific case of external flow turbulent regime where the flow is very chaotic, how will he identify that there is no variation, or be it in terms of temperature or velocity in one particular direction?
First of all, when you talk about flow outside, let's say take the case of a flat plate over which flow is taking place. The flat plate is at a temperature higher than the temperature of the fluid over which it's flowing. So initially, for some length, the flow is going to be laminar, and in which case you know what's the form of the energy equation going to be. So u, which is the velocity in the x direction, the direction of flow, is going to be very large as compared to v, where v is the velocity in the y direction. So the first term is u del t del x, and the second term is v del t del y. So if you think about between U and V, U is larger than V. However, delta T delta X, which is the variation in the X direction, is going to be small as compared to delta T delta Y, where due to the small thickness of the boundary layer, delta T delta Y is going to be more than delta T delta X. So the product of these two will essentially ensure that you won't be able to neglect any of the terms on the left hand side of Navier-Stokes equation, of the energy equation. When you come to the right hand side, then you have the some parameter. I think it's alpha, and then the terms are delta 2t del x square plus del 2t del y square. The first term del 2t del x square denotes essentially conduction in the x direction, whereas del 2t del y square refers to conduction in the y direction. Now, conduction in the x direction is going to be small because from your understanding, you know that because of the flow, most of the heat transfer in the x direction, in the direction of flow, is because of convection, not conduction. However, in delta t delta y, you have Vy to be small and delta y, the thickness of the boundary layer is therefore small. The temperature gradient is large. If the temperature gradient is large, that means the conductive flux is going to be much more than the convective flux. So when you consider the two terms, delta 2t del x square and delta 2t del y square, the first term can be neglected because it refers to conduction in the x direction, which in itself is small. So therefore, your energy equation for flow inside the thermal boundary layer is simply going to be U del T del X plus V del T del Y equals the alpha times delta 2T by delta Y square. However, this is for laminar flow only. When, as you have asked, when the situation becomes turbulent, then you are going to have eddies forming, which are going to which are going to add more heat to be transferred in the flow from the wall, from the plate, because of the formation of eddies. So these additional heat transfer can only be evaluated either empirically or in a much better way if you write the governing equation, and if you non-dimensionalize it, and if you use the analogy, for example, Reynolds analogy or modified Reynolds analogy, which is also applicable in turbulent flow. And through the use of the analogy in a semi-empirical approach, semi-analytical approach, you would be able to obtain an idea, an expression for the heat transfer coefficient even for turbulent flow. So the approach for laminar flow is straightforward. You exactly know what is the governing equation. You should be able to solve it. And once you solve it, you should be able to obtain an expression for Nusselt number. When you go towards the turbulent part of the flow, what you need to do is you have to use analogy, modified Reynolds analogy, to obtain an expression for the Nusselt number for the case of turbulent flow, which I have also covered in the course.
Sir, he says that his question's answer is clear now and he has understood the concept well.
Okay.
We have another question from Ganesh Sridhar, though I feel this question is not directly linked to the course, but he is saying that he is in his final year right now, and he wants to do a project which is related to firefighting robots. So he's asking that will Incropera and Divit be sufficient to get started with it, or if there are some other books that he can refer to for the same.
See, whatever you want to do in heat transfer, you must have your basics very clear, because whatever be the ultimate application, you should have the concepts very clear. In order to clear your concepts in heat transfer, that may be used for firefighting robots or any form of application, heat transfer application, the book of Incropera and Dewitt should be sufficient. But if you want to pick up a specific topic, you probably have to refer to journal papers which have come out mm, specifically describing and discussing the topic, its peculiarities, the technical challenges, state of the art, and the future direction. So all this all these you will have to know from a study of the current literature. But you won't be able to understand anything unless you know your heat transfer. So the undergraduate level course in heat transfer should equip you in such a way that you would be able to read and understand, partly at least, some of the latest research taking place in a specific application. So in order to understand that, Incropera and Dewitt is probably one of the best books on heat transfer available currently.
Sir, Pushpendra Singh is asking that if this course and assignments are sufficient for NPTEL exam and GATE preparation.
Okay, this course, this is a MOOCs course, right? Which we have given, Manikantala?
Yes, sir. It's a MOOCs course.
Oh, was there an exam? There was an exam also in this.
So there will be.
There will be. Okay.
So it's ongoing right now. I think it's in week 3 or week 4.
Yes. So whether it's NPTEL or MOOCs, I think in terms of structure, in terms of evaluation, in terms of exams, there's not much of a difference. In fact, there is no difference. So if you take this course, at the end of this course, you will have an exam, and you will be evaluated, and your performance will indicate like which grade you are going to get. So fundamentally, NPTEL and MOOCs, I don't see much of a difference. Secondly, if I am to teach this course for NPTEL, I would do it exactly the same way, because I don't think heat transfer can be taught differently. The concepts will be different or can be taught differently for in an online platform, whether it's being done for NPTEL or for MOOCs. So to answer your query, yes, definitely this would be sufficient for any kind of online and associated exams in an undergraduate level course.
The Ganesh Sridhar earlier, who was asking about firefighting robots, he's asking that to get started with finite element techniques for heat transfer, is it will Incropera and Dewitt be a good book?
Incropera and Dewitt does not deal with finite element, but if you want to start, if you want to know more about finite difference, then one specific chapter of Incropera and Dewitt is dedicated to the finite difference method. So which is mostly used for non-circular geometries. So whether the problem that you are going to deal with will require finite difference or finite element, that someone else will have to tell you, or you have to read it and find out which method is appropriate. So if you require finite element, then there are many books on finite element which you can find out from just a cursory search of internet, and start reading from there. But if finite difference can serve your purpose, then of course Incropera would be fine. But there are many other programs or softwares which are now available, for example, MATLAB or COMSOL, which would be able to handle situations that you are describing in a much more efficient and in a way which will save a lot of time for you. So you can think in that terms as well.
So there are no more questions.
Okay. So we'll wait for 10 minutes before we were allowed to go. 10 minutes. 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 10 min
So we have one more question where Pushpendra Singh is asking that what is the difference between the corrected length and the normal length in fins?
Corrected length and
Normal length in fins. I think he needs to express his question in a better way to understand.
I'm not getting the question.
Yes. Pushpendra, can you please reframe your question in a better way? Okay, so Sheep Shankar is asking that what are the aspects of research in heat transfer for students?
That's a very broad question. I don't think I'll be able to do justice to this question in the form of an answer in 2 minutes. The field of heat transfer has attracted researchers over many years, close to 100 years or so. Only the type of research has changed over the years. And one of the major research which was which is still relevant now is in the area of energy use, in the area of combustion, where the efficiency of a specific type of heater, type of fuel, type of the design of a burner, everything requires an intimate knowledge of heat transfer, and the efficiency of the entire process can be enhanced by doing specific research in that area. So fuels, combustion, design of equipments that are related to combustion, they form one area of research. And with the thrust of going towards more efficient cars, more efficient engines, and so on, this was one of the very active area for quite some time. Now, one more thing is that with time, the system size has decreased significantly. So we were dealing with large equipment. Now we are coming towards equipments which are smaller in size. So as the size becomes smaller, the heat transfer plays a very critical role. And the heat transfer at small scale has is the new research area where people are putting a lot of effort. Just to give you an example from the chip making, the computer chips, where the circuit density is becoming very dense, very high, and therefore a small amount of heat is generated in an extremely small area, which needs to be dissipated in order to maintain the temperature at a specific level. So we are dealing with a small amount of heat, but since the area is extremely small, the flux is going to be very high. So these kind of high heat flux situations, which are pertinent in thermal packaging of electronic components, has been a very active research area for the last 15 or 20 years. 15 years. And in some cases, the advent or the advancement in chip manufacturing is limited by whether or not we would be able to dissipate the heat from that situation. The third and the upcoming area would be in biomedical heat transfer. So how do we use heat transfer effectively to pinpoint thermal energy at a point inside our body, or extract heat from a tiny machine, tiny probe that has been put into human body at a specific point to create a condition either to dissipate heat or to extract heat, either to cryo destruction of the cells or destruction of the cells by concentrating energy at a specific point. So the dimensions are different, the physics is different, and the way heat transfer is looked and the devices to be designed are going to be different. So these are exotic examples. The thermal maintenance of temperature in spacecrafts when they orbit the Earth or when they enter the Earth's atmosphere is also extremely important. Where you're dealing mostly with radiation in one case, and when they re-enter the Earth, due to viscous dissipation, a large amount of heat is generated. So how do you ensure? How do you design an insulating material? The material construction and the way you insulate the interior capsule such that the astronauts will remain safe is something where again heat transfer plays a very important role. So starting from combustion to microscale heat exchange to biomedical applications to space applications, and of course, we have the application in nuclear reactors where you have to keep the temperature within a certain level. And how do I stop the reaction by by reducing the temperature drastically at a specific point to stop runaway reaction? That safety concern, that's also something which people have put a lot of effort in finding out the exact form of device, which is something I mean, obviously, this is something called heat pipe, which is used to maintain the temperature of the nuclear reactor at a specific level. And the coolant that has been used in that case are molten liquid metals because of the high temperature involved in there and because of the high thermal conductivity. So the design of the thermal system of a nuclear reactor, designing of a system for spacecraft thermal control, designing a strategy for on-chip cooling of modern day computers, and designing heat transfer of biomedical devices are some of the exciting new areas where research in heat transfer is concentrated. But there are many other areas that I did not mention in my answer, which are equally exciting to look at from a heat transfer research point of view.
Sir, I think we have one last question which we can take, where Pushpendra is asking that usually when we have a fin which does not have an insulated tip, we add a correction length to it. But if it's insulated at the tip, then we use the normal length. Why is it done so? Sir,
Oh, yeah, you want to answer?
no, sir.
No, you can if you want to.
Sir, I feel in most of the situations, to simplify the problem, we consider one tip to be insulated. Because though if we have a convective tip, it is a realistic approach. But in most of the problems that we solve, we assume that the fin, one tip has been insulated. Isn't it so?
Okay, that's one way of looking at it. Trina, could you answer? Did you hear what's being discussed? Because of you have some problems with your microphone.
Sir, I think Trina's internet
All
connection
right.
isn't
Okay.
good.
So I agree with what Manikuntala has said, but I would simply like to add a few more sentences to make it more clear. So let's think of this is the fin, the phone is the fin, and this is the tip of the fin, which we can treat as insulated, and therefore no heat is transferred from the tip, and only surfaces which are experiencing a heat transfer are the four surfaces at the four sides of the fin. And this surface, the end surface, is not playing any role in this. Now, let's say for some reason that this tip is not insulated. So you have some area which is available for heat transfer. Now, what is that area? It's the width of the film and the thickness of the film. So I can think of this to be opened up at the middle and being added an area at the top and an area at the bottom. Okay, so if I cut right at the middle of this plane and make them horizontal, so that's the area. So that means W by 2 is being added as the additional length of the fin in order to take into account that the tip of the fin is no longer insulated. So in that scenario, my modified or corrected length would be L plus this thickness by 2. I shouldn't say W. Let's say the thickness is D. So my corrected length would be L plus D by 2. So the corrected area would be from where the heat transfer is taking place. Previously, it was simply this surface, this, and this, the four surfaces. So the top surface had area of L times W. Now the top surface area is going to be L plus d by 2 into W. And similarly for the bottom surface, for the side surface, and so on. So to take into account heat transfer from this face, I'm simply cutting it half, making them straight, making them horizontal, and the additional length that is being added to L is your corrected length.
Okay, so I think we have the time was till 12:45. It's 12:50, but we have
One more
last.
question if there is, otherwise
Yes,
we'll
sir.
wrap it up.
So this is a very ambiguous question where Sheep Shankar is asking that what is the maximum temperature that we can reach by the engineering process?
What is an engineering process? I suppose an engineering process is something which we have created by some means, uh, and it's not the temperature of the sun or anything like that. So I think the maximum temperature that you can reach is when you do the arc welding process, in which you have an arc, and therefore which melts metal. So you have reached momentarily uh, at that location thousands of degrees, 1,000 degrees, 1,500, 2,000 degrees centigrade, and so on. But if you think of the atomic weapons, the hydrogen bombs and so on, those are also man-made, and you can well imagine the temperature at the core of that which has been reached. So if I define by engineering means anything that has been designed and executed by us, so I would say that's the uh, best or worst, depending on your worldview, the highest temperature achieved by man in in any process conceptualized and executed by engineers.
So I think we have no more questions. The students have just expressed their gratitude.
Thank you. So I,
Okay,
I
sir. Thank you,
thank
sir.
the students, and I
Okay.
specifically thank Manikantola and Trina for playing such an integral part in this entire course and in today's session.
Thank you, sir.
So can I leave the meeting now,
Yeah,
Devanshu?
yes, sir. Yes, sir.
All right. Okay. Thank you.
Thank you, sir.